In this video, I'm analyzing the collapse of a high-rise building in Bangkok using Finite Element Method software. The footage of the collapse is dramatic, but behind it lies a structural story worth uncovering. Was it a design flaw, a detailing issue, or something fundamentally unstable in the system itself? Here's the raw footage of the collapse filmed by a worker and shared on social media. We'll come back to this clip later and analyze it by stopping the video. For now, just watch how quickly it all unfolds when hit by seismic waves. Here's a graphic overview of the skyscraper model, shown from top to bottom. The core of the building is slightly reduced at floor 19, where the layout transitions. At the bottom is where we find a soft story, a level with reduced stiffness and fewer structural elements. The columns are each 1 meter by 1 meter in cross-section, with a typical floor height of 5 meters. The foundation consists of pile caps resting on deep piles. The total estimated weight of the construction without piles is around 50 million kilos, resulting in significant vertical and lateral demands on the structure. Here we see the full skyscraper model loaded and calculated with estimated earthquake loads in the FEM software. At the base, you can clearly see the concentration of stress around the pile caps and lower columns. Let's walk through it. The stress distribution is now visible across the structure. As we move up, the stresses redistribute through the vertical elements and floor slabs. Even with simplifications, the analysis required significant resources to resolve all the internal forces accurately. In the next slide, we arrange a less heavy model. This is an isolated view, which means the back part and the lower part of the building, including the soft story. By focusing on this segment, we can see much more detail in how the structure is stressed. Look at the columns at the front, left side now with light blue color. They are under 3 times more stress than the columns just behind them in the corner. The color scale tells the story, going from around 20 MPa or Newton per square millimeter to nearly 60 MPa. These are compressive stresses caused by the immense self-weight of the structure above. While 20 MPa may be within normal limits, 60 MPa approaches or even exceeds the design strength of many concrete columns. This stress concentration is a major red flag. Now let's go back to the original collapse footage and slow it down. Watch closely. We'll freeze the video at key moments. First, you can see cracks forming in the front columns, the light blue column in the previous model. These are the soft story columns. They begin to buckle and fail before any other part of the structure. As the load shifts, the corner columns start to show visible cracking and rotation. This is where the collapse becomes irreversible. It all happens in seconds, but this sequence tells us exactly how the structure gave way, starting at the weakest point and spreading rapidly from there. To test the collapse mechanism, I removed the 2 front columns, the same ones that failed first in the real footage. The result? The structure can't redistribute the load. The stress in the remaining elements jumps now also from 20 MPa to over 60 MPa. That's dangerously close to, or beyond, the capacity of most concrete elements, knowing that the top part has a lower quality concrete. The building has no alternative load path, no redundancy, and just like in reality, the entire structure gives way. This collapse shows how one weak link, like a soft story, can bring down an entire structure. Finite element modeling doesn't just help us explain failures after they happen, it helps us design better, safer buildings from the start. For now, thanks for watching my video. If you found this video interesting, consider liking, subscribing, or leaving a comment below. Let me know which collapse I should analyze next.